Right, so this is the chapter 16, oxidation and reductions. We're going to learn some of those reactions that can be used in some of those technologies. One of them will be the fuel cells. So this is based on the tendency of some element gain electrons and other element to lose electrons. The most common type of fuel cell is the hydrogen-oxygen fuel cell. It's based on the reaction between hydrogen and oxygen. So in this reaction, hydrogen and oxygen form the covalent bonds with one another. A single covalent bond is a shared electron pair. Since oxygen is more electronegative than hydrogen, the electron pair in a hydrogen-oxygen bond is unevenly shared, with oxygen getting the larger portion. In effect, oxygen has more electrons in H2O than the elemental O2. It has gained electron in this reaction. So therefore, in a typical reaction between hydrogen and oxygen atoms gain the electrons directly from hydrogen atoms as the reaction proceeds. In a hydrogen-oxygen fuel cell, the oxygen and hydrogen are separated, forcing the electrons to move through an external wire to get from hydrogen to oxygen. This moving electron constitute an electrical current, which is used to power the electrical motor of a fuel cell vehicle, for example. Fuel cells use the electron gaining tendency of oxygen and the electron losing tendency of hydrogen to force electrons to move through a wire, creating the electricity that powers the car. The definition of oxidation. One definition of oxidation, though not the most fundamental one, is simply the gaining of oxygen. So through oxidation, for example, is the rusting process of some metals. Rust is produced by the oxidation of Rn or Fe. Here the picture shows the rusting of some of those metal Rn. Rapid oxidation, the flame from the oxidation of carbon in natural gas. When you light up or burning the natural gas, so that is the very rapid oxidation. A fundamental definition of oxidation is the loss of electrons, and a fundamental definition of reduction is the gain of electrons. Notice that oxidation and reduction must occur together. If one substance loses electron being oxidized or oxidation, then another substance must gain electrons, reduction or being reduced. There are also these two concepts, the reducing agent and oxidizing agent. Here is the reaction between H2 or hydrogen gas and oxygen gas to produce water. So in this process, we see because hydrogen is oxidized, so we say hydrogen is the reducing agent. And oxygen is reduced, so therefore we say oxygen is the oxidizing agent. Consider our hydrogen oxygen fuel cell reaction. Hydrogen is oxidized, making it the reducing agent. Substances such as hydrogen, which have a strong tendency to give up electron, are good reducing agent. They tend to cause the reduction of other substances. Oxygen is reduced, making it the oxidizing agent. Some substances such as oxygen, which have a strong tendency to attracting electrons, are good oxidizing agent. They tend to cause the oxidation of other substances. A helper for mnemonic for memorize oxidation reduction. One of them is oil reg. O oxidation is loss of electrons, so that means OIL. Reduction is gain of electrons, so we just using the first letter of each word, RIG. There's some other one. Another one is the Leo, the line says gear, loss electrons oxidation, gain electrons reduction. To summarize, oxidation is the loss of electrons, reduction is the gain of electrons, oxidizing agent is the substances being reduced, reducing agent is the substances being oxidized. There's a more general way to identify oxidation reduction is using the oxidation state. In order to identify oxidation and reduction, chemist has devised a scheme of oxidation state to tracking electrons in chemical reactions. In this scheme, which is like a bookkeeping of electrons, all shared electrons are assigned to the most electronegative element. Then a number called the oxidation state or the oxidation number is computed for each element based on the number of electrons assigned to them in the structure. Do not confuse oxidation with ionic charge. Sometimes they will be same, but sometimes we don't have a ionic charge for some element. So a substance need not to be ionic to have the assigned oxidation state. The easiest way to assign oxidation states is to follow the rules for assigning oxidation states. There are 5 rules. Rule 1, 2, 3, 4, 5 are hierarchical. If any rules conflict, follow the rule that is higher on the list. Well, the higher means the number is smaller. So the rule 1 has the highest priority. Rule 1 is referring to the free element. It says the oxidation state of an atom in a free element is 0. So later on we'll see the examples. What do you mean by the free element? The second rule has the second priority. So the oxidation state of a monatomic ion equal to its charge. Rule number 3 is the sum of the oxidation state of all atoms in a neutral compound equal to 0, in a polyatomic ion equal to the charge of the ion. Rule number 4 is helping the rule number 3. So rule number 4 has kind of 2 parts. Part 1 is the group 1 metal have an oxidation state of +1. Group 2A metal have an oxidation state of +2. Group 1, group 2 metal, which means in the periodic table, the leftmost column except the hydrogen will be the group 1 metal. The group 2 metal will be the second leftmost column. So then we also need this last rule has the lowest priority. So in their compound, non-metal are assigned the oxidation states according to their hierarchical table in this table here on the right. The entrance at the top of the table have the priority over the entrance at the bottom. So therefore, if you have to use this rule 5, then the highest priority will be the fluorine. Fluorine has -1, then hydrogen +1, and so on. So now let's practice this 5 rules, then we will see some of those definitions. We'll talk about the free element. So the first question is what will be the oxidation state for Br in the Br2? So we know there are 2 Br atoms in this Br molecule, but in this Br2 you will see the Br is the free element. So therefore the oxidation state using the rule number 1 for both Br atom is 0. So the second question is the oxidation state for this K1 plus ion. So here I just want to show you clearly. The first question is about Br2. There are two Br, then both of them has this number 0. So the second question is the K 1 plus ion. So therefore, the number or the oxidation number, whatever the oxidation state will be the same as the charge. Plus 1 will be plus 1. Then this 3 is not a free element, it's a compound. So therefore, we cannot use rule 1, not rule 3 to get the answer. We have to go to rule 3. So rule 3 just tell you all the oxidation number adding together should equal to something. If something, if you are, the question is about a neutral compound, so you are adding all the numbers together equals 0. So therefore, we can say first we'll give Li plus 1, then the following will be -1. So the D is similar as C. We cannot get answer from rule 1, rule 2. We starting with rule 3. We say this is a neutral compound, so therefore the oxidation number for carbon and then plus 2 times the oxidation number for each oxygen will be 0. So therefore we write something like this: C oxidation state plus 2 times oxidation state of oxygen equal to 0. And obviously in this equation, we have two unknown. We don't know what is this, what is that. So we have to go to the rule 5. So this rule 5 will give you some of those numbers. And then, so this -2 is from that rule number 5 we saw on last slide. Once we get one answer, so we substitute that answer for that question, then we come back to this equation, and then we solving the equation for the other unknown. So this the other unknown. So therefore, that's how we solving the problem like that. And you can see this is a simple equation. So therefore, we can get the carbon ox state equal to +4. You can just indicate the answer like nearby those elements. Make sure those number is for every one atom. Okay, so when you see this +4, -2, so the number or the ox number is for each one atom. So then the fifth question in this practice is SO4 2 negative. So this again, we cannot get any answer using the rule 1, rule 2. So the first two rule 1 and 2 do not give any answer because that does not apply. It's not a free element, not a monatomic ion. Then we will see we have one sulfur, so therefore kind of one sulfur here. So therefore we see one time the S ox state plus 4, so this 4 comes from this 4 here, equal to -2, -2 come from this -2. Again, there are two unknown, so we don't know what is the ox state of sulfur, and we don't know what is the ox state of oxygen. Then we continue rules with other rules. Rule 4, no answer, no help. Then rule 5, we will get O is -2. Then we will come back, put -2 in this equation we get from, sorry, where are we? Oh, sorry, I click on something, then lost our last slide. But anyhow, we get here. So we have this equation, and we said we have to use one other rule to get the one of those unknown. So this now this -2 is for this number, and we get this is from that rule 5. So then we put it back into this equation, and now we only have one unknown. We are solving this the only unknown now. So therefore, we get a positive 6. Then you summarize, you just use one number for solver, then this is for each one O. Okay, so the last one is N2O2. You have to be very careful, otherwise you will make some common mistake. So again, we will set up this equation, and this equation is from rule 3. Now, commonly in the last few examples, you see oxygen, so -2, but not in this one. Okay. So in this one, you go by the priority. So you get this +1 for sodium first, because this comes from rule 4. Rule 4 has the higher priority than rule 5. So therefore, even rule 5 will tell you oxygen will be -2, but before you get that, you already get some answer from rule 4. Rule 4 is kind of dominate or higher priority. So therefore, you will use +1 for sodium, then put it here. You solve this equation, see what will be the O ox state, and it turned out to be -1. So it's not common. All right. So those are the few practice questions to learn how to use the rule to sign the oxidation state for the atoms. And once we have that, and in this example, is using oxidation state to identify the element that is being oxidized and the element that is being reduced in this reaction. Now, this two sentence in red is kind of you want to memorize to using the oxidation state to tell whether they are oxidized or reduced or nothing happens. So once you have this number, and I just compare the number for the element before the reaction, after the reaction. All right. So for this few elements in this reaction, we just go by the rule again. So the first one is calcium solid, which is the free element. So therefore 0 oxidation state for each atom. And then in this water, for H will be +1, for O is -2. In this calcium hydroxide, calcium becomes +2, and oxygen still -2, and here the hydrogen still +1. But not in this H2. H2 is a free element of hydrogen, therefore it's 0. Now you see, for two elements, somewhere the number change. Calcium changed from 0 to +2. So the number increases. And then you can see here, if the number increases, the element is being oxidized. So therefore, we can see calcium increased in oxidation state, so it was oxidized. So some of those H nothing happened. Oxygen nothing happens in oxygen, -2, -2. In some of those hydrogen, like +1, +1, but some of them change. So therefore, we can see some of the hydrogen decreased in oxidation state. Decrease, you know, what I mean, like a decrease is you change from +2 to +1 to 0, so decrease. So therefore, we can see some of the hydrogen has been reduced. You can use this oxidation technique to balance equation. Redox reaction occurs in aqueous solution are usually difficult to balance by inspection and or trial and errors. It requires a special procedure called the half reaction method of balancing. In this procedure, the overall equation is broken down into two half reactions, one for oxidation, one for reduction. Then the half reactions are balanced individually, then added together. So you first assign the oxidation number to all the atoms to determine what is being oxidized, what is being reduced. For example, Al solid plus silver plus ion produce Al3 plus ion and silver solid. We assign the numbers 0 for free element and plus 1 is same as the charge, plus 3 is same as the charge, 0 for free element. Then we can see the oxidation happened to the aluminum or Al, reduction happened to silver. So therefore, we can write this equation into two equations. One will be the oxidation for aluminum. The other one is the reduction for silver. Then we will balance both of them separately and put them together in the last step. In this case, the half reaction are already balanced with respect to the atom, but the charge is not. So therefore, we will balance the charge by using electron. This is the procedure, so you have to follow the procedure. When you balance the atom, we will have the procedure here because the atom is balanced. So we balance the charge by using electron. You just identify on the left, 0 charge, on the right, before we put the electron in, there are 3 plus. We will use 3 electron because 1 electron is -1. So 3 -1 and 3 plus 1, that's also 0. So for the other reaction, the reduction reaction, we were adding electron on the left. Before adding electron on the left, we have 1 plus. After we adding electron on the left, so that becomes 0. 1 plus, 1 minus becomes 0. That is good because on the right, you also have 0 charge. So now we are almost ready to put them together. Before we put them together, make sure both two equations have the same number of electrons. So now, right now, they are not. This first reaction has 3 electrons, the second reaction has 1 electron. What you do, you will multiply some common number, make them have the same number of electrons. So clearly, you will have a 3 and 1. You multiply the 1 by 3. So therefore, we multiply the second equation by 3, and we will have this new equation, a new equation 2. Now we can adding them together. Okay, so now we copy here. We have 2 equations. Both of them has a 3 electron. And then you just adding them together. What happens is the electron cancel out. Then this is the leftover of the reactant. This is leftover of the product. So therefore, our overall equation will be Al plus 3Ag1 plus produce Al3 plus 3Ag solid. To verify the equation balance, you can just do a check. Check how many atoms and how many charge. So this should be both. Everything should be balanced. The Al balance, 1 Al, 1 Al. The Ag is balanced, 3 Ag, 3 Ag. The charge, so like plus 3, or has the plus 1 times 3 is plus 3. And here just 1 of the 3 plus, therefore 1 times 3 is 3 plus. Notice that the charge need not to be 0 on both sides of the equation. It just has to be equal on both sides. So therefore, the equation is balanced. And here is the rule to balance some other equations. Depend on your question. Maybe some of them is simple, like what we saw the last example. Some of them may be very tedious. Also depend on whether our reaction is in acidic solution or in basic solution. And this procedure is for the reaction happening in acidic solution. If it happen in basic solution, here just adding one more step in this step 3. So let's do one example to balance equation in acidic solution. So I have this equation, want to balance it. You can try and so on, but not easy. So therefore, we are using this method in this chapter. We first will separate this equation into two equations. One will be the reduction, one the oxidation. You can do that very quick by using the ox number. So this I1 negative, just -1 because it's a monatomic ion. For this one, you had to use what we talk about using the equations. So we get +6 for Cr, -1 for O. And here become become like a monatomic ion against the 3 plus 3 plus. And this is the I2 is the free element, so 0. Okay. Now we write this equation into two parts. The first part will be this oxidation. The second part will be the reduction. Well, actually, which part you write first doesn't matter. Just write the two equations. Once you have the two equations, you balance them like separately. You first balance the mass, which means balance the atoms. And when you balance the atom, you balance the atom that is not H and O first. So in the equation we get before put these two, they are not balanced. Now we put 2 here to balance the I. In this equation, it's simple. There's only one element. So once you balance the iodine, so everything is balanced in terms of mass, but the charge is not. So let's first balance the mass for both equations. And in this equation, so before we put these two here, we only have a Cr2O7, 2 negative, and Cr3 plus. Therefore, we have to put a 2 here to balance the Cr. Once you balance the atom that is not H and O, you will balance the oxygen by adding H2O. So that's why kind of you get something to use, but you have a lot of procedure to follow. You cannot use some other thing to balance the oxygen. If you see there are 7 oxygen on the left, you don't have any oxygen on the right, you don't use O2 or anything else, you just using H2O water. So if you're adding 1 water, you're getting 1 oxygen. So we need 7 oxygen, so therefore we need 7 H2O. The state for H2O will be liquid. Okay, so now in this equation, so every atom is balanced. There's only one element. We balance that. Now here we kind of balance the oxygen using water, but the problem is if you use water, you are adding like some of those H hydrogen. So therefore, you have to balance the hydrogen by using H plus. So you identify there's 7 times 2, 14 H. There's nothing on the left. So therefore, we are using 14 H plus. Even though H plus does not look like H, but the element. Okay? So therefore, you don't care about H plus or H2O. In H2O, you see the element is H. The element is hydrogen. So therefore, now in these two equations, all the atoms are balanced. The problem is that to balance the oxidation reduction equation, not only you have to balance the atom, you also have to balance the charge. So therefore, we balance the charge by using electrons. So in the first equation here, on the left, we have 2 negative, we have 0 charge on the right. So what you do, you are adding 2 electrons. Each 1 electron is 1 negative. So in that way, you balance the charge. And then for the second equation, you counting carefully how many charge on the right, what is the neutral, charge neutral. So Cr3 plus, you have 2 3 plus, so we have 6 plus. And then here there's 2 negative from this ion. And then 14 plus from this 14H plus. So therefore you have a 12 plus. And you want to reduce the 12 plus to 6 plus. So just using 6 electrons. So that's good. Now these two equations at the bottom of the screen, for each of them, everything is balanced. The atom is balanced, the charge is balanced, the atom is balanced, the charge is balanced. So then the last step in this procedure is adding these two equations together. But before you adding them together, do one more check. make sure both of them have the same number of electrons. So the first equation has 2 electrons. The second equation has 6. You want to make them have the same number, the same least number. You will multiply the first one by 3, which means you multiply all the coefficients. So here we have 2, 1, and 2. So therefore, they become like 2 times 3, 6, 2 times 1, 2, 2 times 2, 3 times 2 is 6. So now this is the, after we multiply the 3 into all the coefficients, we get this new first equation. And then our second equation, we don't need to do anything. We copy here, then we add. So this 6 electron on the left of this arrow, this 6 is on the right of this arrow. After we add them together, so these 2 arrows will become 1 arrow. So therefore, everything on the left can cancel out everything on the right. That's why we cross out the 6 electron on the left of the second equation with the 6 electron on the right of the first equation. Now we have this. Sometimes you might have something same on the left or on the right. Now in this case, we don't have anything the same. So this kind of our final result. But you want to check in your final result is right by just checking every element, checking the charge, and you can do the checking, or let's do it together. See, the first element is iodine. Iodine here on the left, only in this ion. So therefore, we have 6 iodine. Iodine on the right, only here in the I2. We have 3 I2. So 3 times 2 is 6. Hydrogen on the left, just 14H plus. Therefore, we have 14H plus. Again, here you don't pay too much details. You see H plus is same as H. So 14H plus, then here is 7 times 2. So 14H. And then the CR only here on the left, we have CR2, which means we have 2 CR. Now here just clearly 2 CR. Again, you don't mention exactly CR3 plus and CR here, just a CR. So the oxygen on the left is in this ion, so we have 7O. And on the right, the oxygen is in water, so 7 water is 7O. So therefore, all the atoms are balanced. Now we check the charge. Let's see the charge on the left first. So we know this is 6 negative. 6 times negative 1 is 6 negative 6. Negative 6, and then we have the 14 plus, so 8 plus. Then we have 2 negatives, so we have 6 plus. All together on the left, so therefore 6 plus. Then on the right, what is the charge neutral? So therefore 0 charge. Then each CR is 3 plus, so 2 times 3 plus is 6 plus. So therefore everything is balanced. So good or bad, it's guarantee you will be able to balance the equation, but you have to follow the procedure. And this is the procedure to balance the equation, balance the redox reaction in basic solution. So as I said, everything is the same, except in this step 3, you are adding one more step here. Because if the reaction happens in basic solution, you don't want to see the H plus, you have to adding hydroxide to turn the H plus into water. You can keep the hydroxide, and you will see what I mean. So for this equation, and it's a redox, and you want to balance this equation in the basic solution. So again, follow the procedure. You will rewrite this equation into 2 equations. One will be the oxidation, the other one is the reduction. To do that, you can do that very quick, but you to do that like accurately, you will assign the number first. So then again, how you assign the number, you review the previous few slides. So the result is here, and we can see the carbon's number increased from +2 to +4. So therefore, we know something has carbon in it, has been oxidized. So therefore, we write the oxidation is for this cyanide ion CN1 negative, change into this CNO1 negative. For the reduction, where we have something has the manganese, Ma. because Ma, the number for Ma decrease from +7 to +4. Okay, so we have these two equations, and then we are going to balance both of them, balance the atom, balance the charge. So when you balance the atom, you will balance the atom first, then balance the charge. When you balance the atom, you have the procedure. You balance the atom that is not O and H. Then you balance O, then you balance H. Okay. So for this one, before we this highlighted in red water is what we add. So before we add in this water, we know we have carbon and nitrogen, and they are both balanced. So one carbon on the left, one carbon on the right, one nitrogen on the left, one nitrogen on the right. Except there is one oxygen, we don't have oxygen on the left, so therefore we adding one water. One water is one H2O. So therefore you will have one oxygen on the left and also one oxygen on the right. All right. So that's okay. We balance the oxygen. Then later on we will balance the hydrogen. So similar story for this second reaction. Before we add in these two H2O, so we know the Ma is balanced. There's one Ma, one Ma. But oxygen is not. So there are 4 oxygen, 2 oxygen. So therefore we add in 2 water. Okay, now the atom is balanced. I mean, some of those atoms is balanced, but not the H. So to balance the H, you don't use H2 or something else, just using the H plus. So for the first equation, there are 2 H on the left. You are adding 2 H plus here. For the second equation, you will have 2 times 2, 4H. You are adding 4H plus on the left. So 2H plus, 4H plus. Now, if this reaction happens in acidic solution, then you are done, you finished. But this reaction is happening in basic solution. So you don't want to keep this H plus in your equation. And we were adding the right number of hydroxide. What does it mean? The right number? The right number means if you have 2 H plus, you are adding 2 hydroxide. So therefore, you will produce 2 water. If you have 4 H plus, you are adding a 4 hydroxide. So okay, so you already have everything balanced. You adding 2 hydroxide on the right, you must adding 2 hydroxide on the left. That makes sense, right? So that will keep everything still balanced. Even though you change your solution from acidic to basic, but in this way, every atom is still balanced. And then we'll do the same for this second equation. So we're adding 4 hydroxide and 4 hydroxide. Okay, before we do that, we know H plus hydroxide together will make water. So therefore, these two H plus, these 2 hydroxide, we can simply write as 2H2O. We'll do that later. So the same for this equation. We have the 4H plus, we're adding 4 hydroxide on the left, on the right. Now this 4H plus, 4 hydroxide will give you 4 water. So now we summarize what we get so far. And we still have not checked the charge yet, but because we produce water by put H plus and OH together, so therefore we can cancel out some of the water. So for the first reaction, there's 2 water on the right, 1 water on the left. So therefore one of them cancel out. The left will have no more water. The right have only 1 water. Similarly here, so this beginning we have 2 water on the right, 4 water on the left. So 2 of them cancel out, only have 2 left over. Okay, now kind of we clarify our equation. Then we were checking the charge. So the charge, let's see, for this charge, for this first equation on the top, after we cross out the water, because the water doesn't matter, though it don't have a charge. So here is the -1, and I have 2 times -1, so you have -3. And so -3, but this is -2, and this is -1. So -1 plus -2 is -3 on the left. So here the negative one, therefore you plus 2 electrons to also give a -3. That's why we put a 2 electron here. And then the equation, the second equation, you will check the charge also. So how many charge on the left? -1. Now how many charge on the right? 4 times -1, -4. So therefore you want to add in like a 3 electron on the left. All right, so now these two equations, everything is balanced. The atom is balanced on that by themselves. So now we kind of want to balance the something between them, which means the first equation has 2 electrons, the second equation has 3 electrons. You want to have the least common number for both of them. So that will be 6, right? So therefore, we will multiply the first equation by 3, multiply the second equation by 2, and we have this. What this means is you will multiply every coefficient by this same number for the reactant, for the product, right? So you know those guys, we don't have a number means 1, we don't have a number means 1, 3, 2, and we call the coefficient. So you make sure you multiply every coefficient. Okay? Then you will see you will have the same number of electrons in both equations. So 6 electron here, 6 electron here. Even though this is in the first equation, this in the second equation, but when you add in them, they become one equation. So just pay attention to are they on the left or are they on the right? So that's pretty good. And then we can also see in this example, there's also water comes out. So there's 3 water here, 4 water here, cross out become 1. And also the hydroxide. So 6 and 8, so 8 cross out and give you 2. So now you clarify everything, just write whatever left over. So therefore we have a 3 cyanide, a CN1 negative, 2 permanganate, 2 MnO4 negative called permanganate, and water, then this. If this balanced, you check it, okay? Just make a list for carbon, for nitrogen, for Mn, for oxygen, for H, for charge. And so for carbon, there are 3, okay? Coming from these 3, or kind of 3 times 1. For nitrogen on the left, also 3. So 3 here. All right. So the charts probably sometimes you cannot see. Oh, let's see. For Mn just 2 Mn here and 2 Mn here. For oxygen, there are 2 of them has oxygen. Water has oxygen, then this permanganate has oxygen. So you have 2 times 4 is 8, and then you have 1. So this 9 comes from 2 times 4 plus 1. On here, this 9 comes from 3 times 1 is 3 plus 2 times 2 is 4, and plus 2 times 1. So that's 6 plus 3, also 9. So you can see here 3, 1, 2, and 2, and 2, and 1. For the charge, do the same. And so the charge here, this guy will give you -3, because that is 3 times -1, right? And this count will give you -2 because 2 times -1. So therefore, altogether, -3, -2 is -5. And then on the right, so this give you like a kind of 3 times -1. And then this is the 2 times -1. So again, you have -3 and -2. So -2, -3 together, -5. So everything is balanced. We have the activity series. You can use it to predicting the reaction, the spontaneous or not. So just memorize some of those rules. the activity series of matter leads to matter in order of decreasing tendency to lose electron. What that means is the matter on the top lost electron easier. The matter at the top of the list have the greatest tendency to lose electron easier. They are most easily oxidized and therefore the most reactive. The matter at the bottom of the list have the lowest tendency to lose electron. They are the most difficult to oxidize and therefore the least reactive. And we still keep this table here and see this tendency here. So then we can use it to solving some problem. So each reaction in the activity series is an oxidation half reaction. What that means is all those reactions is written here is oxidation because they all tell you lost electron. So the half reaction at the top are most likely to occur in the forward reaction. The half reaction at the bottom are most likely to occur in the reverse reaction. If we pair a half reaction from the top of the list with the reverse of the half reaction from the bottom of the list, we get a spontaneous reaction, which means we don't have to use any energy. The reaction will go, and the reaction will go, then will give you energy. Usually you can harness the energy as electricity. So here is one example that is spontaneous. The reaction happened between magnesium and copper. So we use magnesium metal, then the copper initially is the copper ion, copper 2+ ion. So by the natural tendency of the magnesium reaction will be on the top, the reverse of copper reaction will be at the bottom, so therefore this reaction is spontaneous. And so therefore you put the magnesium metal in this copper solution. So gradually the magnesium will be lost into solution, kind of eat away. And then the copper in the solution deposit on the metal. You kind of those copper reduced to metal or copper ion reduced to metal deposit on the metal. If you do the reverse, if you use copper metal and put in a solution of Mg2+ solution, nothing will happen. You can make that happen by using electricity. All right, so therefore we can just use that table to determining for a given reaction, if that reaction happens spontaneously from left to right. So for the first one, you want to predict if the Rn solid plus magnesium 2+ produce Rn 2+ ion, then magnesium metal is that spontaneous. Well, so the reaction involves oxidation of Fe. So we have that equation with the reverse reaction above in the activity. So therefore, this is not spontaneous. The second part is we have the reaction involve Fe. So Fe being oxidized, and which is on the top of the reverse of lead being reduced. So therefore, we can say this reaction will be spontaneous. And then one particular prediction is predicting whether metal dissolve in acid, because acid is also in that table on the list. So most acid dissolve metal by the reduction of H+ ion to the hydrogen gas and the corresponding oxidation of the metal to its ion. But there is one special acid. There may be some other acid, but with the common one special acid will be the nitric acid. So nitric acid kind of even stronger oxidize some of the metal. We'll see if we need to study that. So metal above H2 on the activity series dissolve in acids, while metal below the H2 do not dissolve in acid. So the important exception to this rule is nitric acid, which through a different reduction half reaction dissolve some of the metal below H2 in the activity series. So here is one example. The metal is on the top of the H2. So therefore, this metal, which is the zinc, it will dissolve in the usual acid like HCl or HBr, or even the acetic acid. So what happens is the zinc being oxidized into zinc 2+ ion, and then the reverse of H2 oxidized is the H+ being reduced. So therefore, we see if zinc is on top of this reverse of this second reaction, then the reaction will happen spontaneously. And you check the activity series, that is true. And that's why you see the reaction here. The gas bubbles, just the H2 gas. And then this question is about does Cr, which is chromium, dissolve in hydrochloric acid? To answer the question, we'll say is chromium on top of H2? If it is, it will dissolve. Otherwise, will not. So then we can use those spontaneous redox reaction to make a battery called the voltaic cell. So the electrochemical cell that create electrical current from a spontaneous reaction is called voltaic cell. Voltaic cell or galvanic cell. So this name after some scientists, Waltoni and Galvani. So those like 400 years ago, some of those Italian scientists discovered the electricity from the muscle of a frog. So in the voltaic cell, in the next figure, the following reaction happens. So a solid strip of zinc is placed into a zinc+ ion to form the half reaction. And then the solid strip of copper is placed into copper 2+ ion to form the second half reaction. So we know the reaction, if you put them together, they will happen together. But you don't want to happen like just directly the electron go from zinc to copper ion. You want to harness that by using those kind of device. So the device I will show you in this picture. You don't insert the zinc into this solution. Otherwise, you will see the electron just lost from zinc to the copper ion in the solution. You want to use this natural tendency, you just separating these two reactions into half, in two beakers. So the oxidation will happen in this part. This part they call electrode. So the electrode is kind of the terminal in your common battery. We have the anode and the cathode. So the anode is where the oxidation happens. And cathode is the electrode, the reduction happens. And then those signs for the batteries, like the anode has the negative sign because the electron flow out from the anode. So the metal strip where that happens is called the cathode and has a positive sign. So this part will be the positive. If your battery, so that's call your battery. Okay, so now we really harness, control the tendency. We force the electron going out. You still want to go to the lower potential place. So therefore, go kind of you have a waterfall. You can use the water for to make a hydro to make some of the electricity powers. But that's different story. So using electricity to do chemistry is kind of, we want to reverse some of those reactions. So what we just say in a voltaic cell, a spontaneous reduction is used to produce electrical current. In electrolysis, the electrical current is used to drive otherwise non-spontaneous reactions, which is very useful too. So an electrochemical cell used for electrolysis is called the electrolytic cell. Um, so we compare or contrast the type of cell for the hydrogen system. And so this is spontaneous, so produce electricity. We can use this equation in a voltaic cell. Now the problem is kind of a chicken and egg. Where you get the H2 gas? So one thing about you can get the H2 gas from the decomposition of H2. So probably that will be a very easy, very good way to produce like the energies. Probably we can use like a nuclear power or something to get the H2. Then we use the H2 we get to produce electricity or to drive our car. But okay. So here is the picture for the setting of this second reaction. You can see we use battery, use electricity to drive in the reaction, and you will produce these two gas. One is the O2 gas, the other one is the H2 gas. You know which one is which is by using the coefficient. So we produce more H2 and only half of the O2. You can see here on the top, this empty place is for the gas. And one of the problems associated with the widespread adoption of fuel cell is the scarcity of hydrogen. Where the hydrogen to power to use the fuel cell is going to come from? A solar or wind powered electrical cell can be used to make hydrogen from water. Then the sun is shining or when the wind is blowing. That's a good idea. You can use them in the spacecraft. Then the hydrogen can be converted back into water. Then they can drink the water. So hydrogen made in this way probably used to power fuel cell vehicle. Another application is do the so-called plating. So we know like some of those metals is very attractive, but they are very expensive. For example, silver. Silver can be oxidized in this setting. So we connecting this silver metal to the positive end of the battery. Then we connecting some other metal to the negative end of the battery. For example, this some other metal. Then we were coating the other kind of cheap metal with silver. All right, so this is the end of this chapter.